Welcome to the Explainer. Today, we're diving into a question that's fundamental to our modern world, yet most of us never really think about it. How does a photo, a message, or a video actually travel through the air to your device? Well, the answer is a beautiful piece of engineering called digital modulation. We're going to unpack the core principles using Andrea Goldsmith's classic textbook Wireless Communications as our guide to reveal the invisible language that powers our connected lives.
So let's really dig into that core question. On one hand, you've got digital information. It's clean, it's precise, it's just a long list of ones and zeros stored on your device. On the other hand, you have the physical world, the air around us, which can only carry smooth, continuous analog waves, kind of like ripples in a pond. Now, these two things seem totally incompatible, right? So how do we translate that perfect, abstract digital code into a messy, physical signal that can fly through the air and be perfectly put back together on the other side? That translation process, that's digital modulation. And honestly, it's one of the most brilliant inventions of modern engineering.
To really understand how this works, we're going to follow a 5-part journey. First, we'll start with a foundational idea. How can we represent signals in a way that makes sense mathematically? Think of it like learning the alphabet of our wireless language. Then, in parts 2 and 3, we'll explore the main verbs of that language, the different ways we can change a wave to encode information. After that, in part 4, we'll look at a crucial real-world problem: how to send these signals one after another at insane speeds without them just blurring into each other. And finally, we'll tackle the last piece of the puzzle, the incredible challenge of keeping the sender and receiver in perfect time, right down to the nanosecond. So let's get started.
Okay, Section 1, Signals in Digital Space. Before we can even begin to send data, we need a way to think about it. We need a common language. I mean, when you're dealing with invisible radio waves that are oscillating millions or even billions of times per second, you can't just look at them. You need a better way to represent them. And that's where a powerful mathematical idea called signal space analysis comes in. It's a way for engineers to escape the complex physics of waves and instead work with simple, intuitive geometry.
So, what exactly is a signal space? Well, imagine a city map. Every single location on that map has a unique address, a unique set of coordinates, right? A signal space is just like that, but for signals. It's a mathematical map where every possible signal we might want to send gets its own unique coordinate, its own address. So instead of dealing with some complicated waveform that changes over time, we can just say, hey, I'm sending the signal located at this specific point on the map. The dimensions of this map are based on the fundamental properties of a wave, which we'll see in a moment. So for every unique string of bits we want to send, like 01 or 1111, we assign it a unique point on this map.
And here is where this idea becomes so incredibly powerful. This whole framework transforms the problem of wireless communication into a problem of geometry. The collection of all the possible signal addresses we can send is called a signal constellation. That's the map you see right here. And on any map, what's the most important thing? It's the distance between locations. Here, that simple geometric distance, the Euclidean distance between 2 points, has a direct physical meaning. It tells us exactly how different two signals are. The further apart 2 points are on this map, the easier it is for a receiver to tell them apart, especially when real-world radio noise is trying to corrupt the signal and blur the addresses.
This slide perfectly illustrates the receiver's challenge and its incredibly elegant solution. Let's just walk through it. In step 1, the receiver hears a signal. But the signal it gets isn't the perfect one that was sent. Nope, it's been corrupted by noise during its journey. In step 2, the receiver takes this corrupted signal and plots its location on its own copy of the constellation map. Now, because of the noise, this point isn't going to land exactly on one of the predefined cities. It'll be somewhere in the countryside between them. So, in step 3, the receiver does something really simple. It just measures the distance to all the valid cities on the map and finds the closest one. Finally, step 4, it makes a decision. It just assumes that the closest city was the one the transmitter was originally aiming for. This simple rule, pick the closest, is called the maximum likelihood decision criterion, and it is the optimal way to decode signals in the presence of common noise.
Okay, so we have our map, but how do we actually create the signals that correspond to these points on the map? I mean, how do we physically generate a wave that's going to be interpreted as a specific address? We do this by systematically changing the most fundamental properties of a simple radio wave, which we call a carrier wave. We can change its amplitude, which is just a fancy word for its power or its strength, or we can change its phase, which refers to its position or timing within its repeating cycle. Or, as we're going to see, we can do both at the same time.
These different methods give us different ways to draw our city map, and each one has its own pros and cons.
The most straightforward method is called pulse amplitude modulation, or APM. The M just stands for how many possible levels there are. In this technique, the only thing we change is the strength or amplitude of the signal. So for example, to send 2 bits at a time, we could define 4 different power levels. The lowest power could represent the bits 0, 0. A slightly higher power could be 0, 1, the next level 1, 1, and the highest level 1, 0. On our constellation map, this is like placing all our cities along a single straight road. It's super simple to create and to decode, but it's not very robust. A small burst of noise could easily push a signal from one level to the next, causing an error. It's also only using one dimension of the two-dimensional space we have available.
A more robust and frankly clever method is phase shift keying, or MPSK. With this technique, we do the opposite. We keep the signal's amplitude, its power, exactly the same for every single symbol. Instead, we encode information by shifting the phase of the wave. Think of it like a clock face. A signal starting at the 12 o'clock position could be 0, 0. A signal starting at 3 o'clock, which is a 90-degree phase shift, could be 0, 1. At 6 o'clock, 180 degrees could be 1, 0, and so on. The big advantage here is that every point has the same energy, which makes designing power amplifiers much, much simpler. On our map, this arranges all our constellation points in a perfect circle. A really common version of this with 4 points, like the one shown here, is called quadrature phase shift keying, or just QPSK. Now we get to the technique that truly powers our modern high-speed world, quadrature amplitude modulation, or MQAM. The name says it all. This method is so powerful because it's a hybrid. It combines the last two ideas. We vary both the amplitude and the phase of the signal at the same time. This is what finally lets us use the full two-dimensional potential of our signal space map. Instead of just a line or a circle, we can now create a dense grid of constellation points, kind of like a city block. And by having more points packed into the same space, each individual signal can carry more bits of information. This is the secret behind how modern systems like Wi-Fi and 5G are able to achieve such incredible data speeds.
And this is one of the most important trade-offs in all of wireless engineering. This incredible data density comes at a price. There's no free lunch here. Every single time we want to pack more points onto our map to send more bits with each symbol, we have to make a choice. We can either crowd the points closer together, which makes them way more vulnerable to noise, or we can crank up the transmitter power to keep them spaced apart. The engineering rule of thumb is that for every 2 additional bits you want to send per symbol, say going from a 4x4 grid of 16 QAM to an 8x8 grid of 64 QAM, you need to increase your transmitter power by about 6 decibels. Now, a decibel is a logarithmic scale, so 6 dB means quadrupling your power. That's a huge cost, and it's the constant battle engineers face, the thirst for more data versus the limitations of power, battery life, and interference. So far, we've focused entirely on changing the amplitude and phase of a single carrier wave. But there is one more fundamental property of a wave we can mess with. Its frequency, which is just how fast the wave oscillates. This leads us to a completely different family of modulation with its own unique characteristics. This slide lays out the conceptual difference really clearly. On the left, with AM and PM, we have one radio carrier, and we're just changing its shape. It's kind of like singing a single note, but just varying its volume and tone. On the right, with frequency shift keying, or FSK, we're not changing the note, we're singing completely different notes. We literally switch between different carrier frequencies. A high-frequency signal could mean 1, and a low-frequency signal could mean 0. The receiver's job is in some ways conceptually simpler. It doesn't need a complex map, it just needs a bank of filters to listen and figure out which frequency is currently being transmitted. This can be very robust, but it tends to use up a lot more radio spectrum than QAM.
Now, a key refinement to FSK is making sure that the transition between frequencies is smooth. See, if you abruptly jump from a low frequency to a high one, it creates a sudden discontinuity in the phase of the wave. This is the radio equivalent of slamming on the brakes and then the accelerator in a car. It's a jarring event that creates a lot of unwanted energy or spectral splatter that can interfere with other users in adjacent radio channels. And since radio spectrum is a scarce and expensive resource, this is a really bad thing. The solution is continuous phase FSK, or CPFSK. This uses some clever mathematics to ensure a perfectly smooth phase transition between symbols, resulting in a much cleaner, more compact, and neighbor-friendly signal.
All right, section 4. So far, we've been talking about sending these symbols, these points on our constellation map, as if they're these isolated one-off events. But in reality, we're sending a relentless high-speed stream of them, one after another, millions of times per second.
This is like trying to speak incredibly fast. If you don't pause between your words, they start to slur together and become unintelligible. The exact same thing happens with radio signals, and it introduces a new and very significant challenge.
This problem is called intersymbol interference, or ISI. When symbols are transmitted in rapid succession, the energy from one symbol's pulse doesn't have time to fully die out before the next one begins. It just lingers and spills over into the time slot that's reserved for the next symbol. You can think of it like dropping pebbles into a pond too quickly. The ripples from one pebble interfere with the ripples from the next, and it just creates a confusing mess. For a digital receiver, ISI is a total disaster. It effectively blurs our beautiful, crisp constellation points, making it impossible for the receiver to tell which city was the intended target.
The solution to ISI is one of the most beautiful ideas in digital communications. It involves mathematically designing a special pulse shape that satisfies what's known as the Nyquist criterion. Just look at the pulse shape on this slide. It's designed to have a magical property. At the exact instant in time that the receiver needs to sample it, that's represented by that central dashed line, the pulse is at its maximum value. But if you look at the sampling instance for every previous and every future symbol, its value is precisely 0. This means that when the receiver looks at the signal at the perfect moment, it only sees the energy from the symbol it cares about. The interference from all the other symbols has been perfectly canceled out. It's an incredibly clever way to pack symbols tightly together without them interfering. A very common pulse that does this is called the raised cosine pulse.
We're almost there. We now have our constellation map, our methods for creating the points, and these clean, ISI-free pulse shapes to send them in a stream. But one final, absolutely critical challenge remains. All of this relies on one huge assumption, that the transmitter and the receiver are in perfect synchronization with each other. Without this, the whole beautiful system just falls apart.
See, there are really two clocks that have to be perfectly aligned. First is the carrier phase. The receiver has to perfectly reconstruct the phase of the original carrier wave. If it's off by even a few degrees, it's like trying to read our constellation map while it's spinning. A point that was sent in the top right quadrant might appear in the top left, leading to a huge cascade of errors. Second is the symbol timing. The receiver's sampling clock must be perfectly aligned with the incoming stream of symbols. It needs to sample at the exact peak of each pulse to get the maximum energy and, crucially, to hit those 0 ISI points we just designed. If it samples a little too early or a little too late, it's going to see interference from other symbols, and the whole benefit of our pulse shaping is just lost.
So how is this incredibly precise synchronization achieved in the real world, inside your phone or your Wi-Fi router? Well, it's not set once and forgotten. It's a continuous, dynamic process. The receiver uses sophisticated algorithms, often based on that same maximum likelihood principle we saw earlier. It constantly analyzes the incoming signal itself, looking for patterns and properties that give it clues about the transmitter's phase and timing. It's basically a feedback loop. It listens, it estimates the error between its own internal clocks and the incoming signal, and it makes tiny corrections to stay perfectly locked in sync, even as conditions change. It's an incredible feat of real-time signal processing.
And that brings us full circle. As Andrea Goldsmith says so elegantly in the source material, the receiver structure and decision criteria are derived from a geometric interpretation of signals. This entire complex process of encoding, detection, pulse shaping, and synchronization, it all ultimately boils down to that one powerful unifying idea we started with, the geometry of signals in an abstract space.
So let's quickly recap our journey today. We learned that to send digital bits through the analog world, we have to alter the fundamental properties of a carrier wave, its amplitude, its phase, or its frequency. We discovered that engineers don't think in terms of waves, but in terms of a geometric map called a signal constellation, which allows a receiver to easily detect which bits were sent. And finally, we saw that to make it all work in the real world at incredibly high speeds, you need to employ clever pulse shaping to prevent signals from blurring together, and sophisticated algorithms to maintain the perfect synchronization that the whole system depends on.
We really hope this deep dive has given you a new appreciation for the incredible science and engineering that's packed into every single wireless device you use. If you found this interesting and you want to see more explainers like this, please take a moment to subscribe to the channel and like this video. It really does help others find our content. And if you have any questions, or if there's another complex topic you'd like to see us break down, please let us know in the comments below. We read all of them.
We'll leave you with a final thought to ponder. This entire system of global communication works by creating and navigating a purely abstract mathematical space that's governed by elegant rules. It really makes you wonder, What other invisible systems, what other hidden languages and structures are all around us, quietly shaping our world, just waiting to be understood? Thanks for watching.